Welcome to This Explainer. Okay, let's dive right into things today. We are taking a little journey to uncover the true cosmic mechanics of gravity, mass, and weight. It's a completely fundamental part of how our universe operates, but honestly, it's something almost all of us get wrong every single day. So let's start right off the bat with a somewhat personal question. Is your bathroom scale lying to you? I mean, think about it for a second. You step on it in the morning and you probably casually say to yourself, well, I weigh 60 kilograms. Well, I hate to be the bearer of bad news, but from a strict physics standpoint, that sentence, it's literally entirely incorrect. Your scale is actually measuring one thing, but telling you another. It completely blurs the lines between two totally different scientific concepts. And that brings us to a really crucial distinction we've got to clear up before we go any further. Right, so here is the core difference. We've got mass on one side and weight on the other. Mass is the actual quantity of matter in an object. It's the physical stuff you're made of, the whole shebang, and it is strictly measured in kilograms. Your mass doesn't change at all unless you literally lose or gain physical matter. Weight, though, totally different beast. Weight is actually the localized, invisible force of gravity acting upon that matter. And because it's a force, it's measured in newtons, not kilograms. So, when you say I weigh 60 kilograms, you're actually giving your mass, but you're calling it a weight. Crazy, right? So let's move right into section 1, how gravity actually works. To really get a handle on your weight, we absolutely have to understand the invisible force creating it. We casually tend to think of gravity as something that just simply pulls down. But, well, down is completely relative. Objects with massive amounts of matter, like our Earth, create these really strong forces of gravity. But if you look closely at the direction, the force of gravity doesn't just pull down. Actually, scratch that, it acts directly towards the center of the large mass. It's like a giant magnet in the core. And this perfectly explains why people standing way down at the South Pole don't just fall off into the void of space. The gravity acting on them is pulling them straight toward the Earth's core, exactly the same way it does for someone at the North Pole or literally anywhere else on the globe. But, gravity isn't just this constant, inescapable net everywhere you go. Distance matters immensely. Gravity's strength actively decreases as you move further away from a large object. Imagine you hop into a spacecraft and fly directly away from Earth. The physical matter that makes up your body, your mass in kilograms, stays exactly the same. But the force of Earth's gravity acting on you, it actually shrinks the further out you get. Because that gravitational force gets smaller and smaller, your actual weight decreases, even though your mass remains totally unchanged. Which brings us to section 2, understanding contact force. Okay, so if gravity is constantly pulling our mass toward the center of the Earth, why on earth aren't we plummeting straight through the floor right now? Good question, right? Think about someone simply sitting on a chair. It looks like absolutely nothing is happening, but physically, there's actually an intense battle of forces going on. Your weight, that downward force of gravity acting on your mass, is pulling you towards the Earth's center. But you aren't moving through the chair because the solid surface of the chair is pushing back up on you with an absolutely equal force. This upward push is what we call the contact force. So the big takeaway here is that when an object is resting on a surface and not moving, the upward contact force perfectly equals the downward force of your weight. The forces are completely, perfectly balanced. But what happens when things aren't perfectly balanced? Well, as you can see, we have an imbalanced force in action here. Imagine a heavy Jeep sinking into soft sand. In this scenario, the weight of the vehicle, its downward gravitational force, is much, much greater than the contact force the shifting sand can actually provide, pushing back upward. Because the weight completely overwhelms that contact force, the balance is broken, the surface gives way, and the object sinks. It's just a perfect visual representation of what happens when that downward pull totally wins the tug-of-war. Now, let's jump into section 3, calculating your cosmic weight. Now that we kind of understand this constant tug-of-war between gravity and contact forces here on our home planet, it's time to expand our scope a bit and look at the actual math behind gravity. And hey, don't let it intimidate you, it's super simple. We can demystify it using a really basic formula triangle. To find your weight, the equation is incredibly straightforward. Weight, which we represent with a capital W, is equal to your mass, lowercase m, multiplied by the localized strength of gravity. Here on Earth, the strength of gravity pulling on every single kilogram of mass is approximately 10 newtons. So, Earth's gravity strength is 10 newtons per kilogram. To find your weight on Earth in newtons, you just take your mass in kilograms and multiply it by 10. Simple as that. Let's just quickly walk through these 3 simple steps so you're totally empowered to calculate your weight anywhere in the cosmos. Step 1. Find your actual mass in kilograms. Remember, this is the unchanging amount of matter inside you. Step 2. Find the gravity strength of whatever planet you happen to be on, and that's measured in newtons per kilogram. And step 3, just multiply them together. Mass times gravity equals your weight in newtons. Once you grasp this, it's pretty fascinating. Your mass is your universal constant, but your weight, it's highly variable. It depends entirely on where you decide to park your spaceship. And to show you exactly how variable that weight is, let's take a quick little tour of our solar system. The strength of gravity is absolutely not 10 newtons per kilogram everywhere you go. No way. The gravitational pull fluctuates wildly because it depends entirely on the mass of the celestial body you happen to be standing on. Simply put, a bigger planet means a much bigger pull. Let's compare some of the most dramatic differences out there. Earth, as we know, sits comfortably at 10 newtons per kilogram. But look at Jupiter. Because Jupiter is incredibly massive, it wields this crushing gravitational grip of 25 newtons per kilogram. Now, look at the completely other extreme, our moon. Because it has a much, much smaller mass, its gravitational pull is incredibly weak, just 1.6 newtons per kilogram. So, let's see what that actually means for a human body. Let's take a person with a steady mass of 45 kilograms. On Earth, we multiply that 45 by 10, giving them a weight of 450 newtons. Easy enough, right? But transport that exact same person with the exact same 45 kilograms of mass all the way to Jupiter, and their weight skyrockets to an immense 1,125 newtons. They would feel incredibly heavy, probably struggling just to stay upright against the contact force. Now, safely transport them to the moon, multiply by 1.6, and their weight plummets to a mere 72 newtons. This is exactly what perfectly explains why the Apollo astronauts could effortlessly bound and skip across the lunar surface. Their mass hadn't changed a single bit, but the localized force of gravity acting on them was just absolutely tiny. Let's just really quickly survey the rest of our cosmic neighborhood, just to show how dependent your weight is on your location. Here's kind of a quirky fact. Despite being a massive gas giant, Saturn's gravity strength at its theoretical surface actually matches Earth perfectly, at 10 newtons per kilogram. Neptune is just a tiny bit stronger at 11. Venus and Uranus are slightly weaker than Earth, sitting at 8.9 and 8.7. And if you took a trip to Mars or Mercury, you'd feel quite light, as both exert a really weak gravitational pull of just 3.7 newtons per kilogram. Which brings us to our final thought for today. Now that you know the absolute truth about mass, weight, and the invisible forces constantly pulling us towards the center of planets, it's time to apply this to yourself. Knowing your exact mass in kilograms, the true unchanging amount of matter that makes you, well, you, what would your weight be right now if you were standing on Jupiter? Just take your mass and multiply it by 25. The sheer size of that number might actually shock you. So the next time you step onto a bathroom scale, remember, it's not measuring how much of you there is. It's just measuring how hard the Earth happens to be pulling on you today. Keep questioning, keep learning, and I'll catch you in the next explainer.